The final experiment was created by Will Duffy, with the goal to disprove the flat Earth theory. He took a group of flat earthers and globe earthers to Antarctica to see the midnight sun. It is a phenomenon impossible to see in a flat Earth, so this experiment, observation, or whatever you want to call it, should finally settle the debate. So, the group arrived in Antarctica. They set up several cameras, they did some live streams to prove they were there, and to the surprise of the flat earthers, they could see a midnight sun, a sun that does not set.
All right, guys, sometimes you are wrong in life. You brought me here, and it's a fact. The sun does circle you in the south. So what does that mean? You guys are gonna have to figure that out yourself. Don't listen to my beliefs or my opinion. It shouldn't matter to you, but at least you should be able to accept that the sun does exactly what these guys said as far as circles the southern continent.
But the flat earth community didn't take it so well. They don't like the results, and they are questioning all the videos. They are looking into any tiny detail to claim fake.
Unbeknownst to most, for the past few years, portable, panoramic, 360-degree LED studio setups now exist and are being used for Hollywood productions like The Mandalorian and many others.
The common claim is that all the videos were recorded in a studio, with big LED screens projecting both a distant landscape as well as a faked sun. However, the final experiment used multiple cameras, including 360 degrees cameras. Two of these were operated by Dave McKeegan and Will Duffy, and recorded simultaneously from different points. This is interesting because we have two different points of view for the same moments of time. If we have two cameras looking at the same object, and if we know the distance between them and the direction in which they are looking at, it is then possible to estimate the position and distance to the objects. When looking at a distant object, like a mountain or the sun, the sightlines from both cameras will converge very far away. However, if a screen displays the same landscape, even if the apparent size is correct, the sightlines will converge on the physical object displaying the landscape, the LED screen, which is a close object although it is showing a very distant landscape. If the videos were filmed in a studio with LED screens, then the sightlines should reveal the actual location of the screens. So let's take the 24-hour time lapses from McKeegan and Duffy. From McKeegan's camera we can see Duffy's camera, and vice versa. We can now see everything else, although at different positions of the image. Let's align both images so the cameras are looking at each other. We're going to call that 0 degrees. When the cameras are facing each other, their azimuth is 0 degrees. Both cameras cover 360 degrees in horizontal. They cover all the space around them, but more importantly, we know the size of the images. So we can calculate how many degrees represent 1 pixel. It's nearly 0.1 degrees per pixel. So counting the number of pixels from the center of the image to a selected object, we can calculate how many degrees to the left or to the right that object is to respect to the 0. And the ideal precision we have is at least 1 pixel, that is 0.1 degrees. Now, we still need to know the distance between both cameras. Here we have Dave and Will walking from one camera to the other. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. About 15 steps. One step is less than 1 meter, about 60 or 70 centimeters. So 15 steps, I think we can round them to about 10 meters. So there it is. Now we can pick any object and try to see if we can pinpoint it in the images. So this is Wes Wallis' sundial. It is 96.8 degrees to the right from McKeegan's camera, and from Duffy's camera it's 27.7 degrees to the left. We can draw the sightlines from each camera. At the point where both lines cross and overlap, that's where the object was. Quite close to both cameras. But let's have a closer look. I didn't just trace a line. I took into account the theoretical precision we have of 0.1 degrees. So these are two cones of plus minus 0.1 degrees. The cones widen as we go farther from the cameras. Both cones do not just cross in a single point, but they overlap in a small area. This is the precision we have to pinpoint an object. Okay, let's pick another object. Let's look at Tom's sundial. 127 degrees right from McKeegan's, 31 degrees left from Duffy's. And there it is, a bit further away than Wally's sundial, about 20 meters from Duffy's camera, about 10 meters from McKeegan's camera. Hey Eliud, it is a large object, so let's take the door as a reference. It is 162 degrees left from McKeegan, nearly at the back of the camera, and 11 degrees right from Duffy's. It was about 20 meters away from the cameras, and we can see that the precision for the position is a bit less than 1 meter. Let's check now for Geran's solar tracker. 98 degrees left and nearly 44 degrees right. And there it is. So far so good. All these positions were close to the cameras, within a range of 20 meters or so, and we have reasonable results. This method to pinpoint objects from the lines of sight of two cameras is working perfectly fine. Let's check it now for the landscape, and see whether it is far away or there is a close screen displaying it. So this is Mount Roseman. It is 9.7 degrees right from McKeegan's camera, 170 left for Duffy's. And there we go. Well, it seems it's a bit farther than 20 meters. 100, 200. There, 500 meters, the lines of sight start to overlap. But that's only the lower bound. Let's see where the lines stop overlapping to have a proper estimation. 1 kilometer. 2 kilometers. 3. 4, and still overlapping. We could go on, but the main take is that the Mount Roseman was something between 500 meters and infinity. Well, that's quite a large studio, isn't it? What does that mean? Simply that the mountains were too far away. We don't have enough precision to make an accurate estimation of anything that far away with this setup. Last but not least, let's check the midnight sun. Now, something to note about the sun is that it's actually not as big as it seems in the videos. What we see here is basically the glare produced by the sun on the optics of the cameras. Even if both cameras are the same model, an Insta360, the cameras themselves are different devices, in different orientations, so the glare and distortions produced by each camera is different. The apparent size of the sun is actually 0.5 degrees. That's about 5 or 6 pixels. That's how small it really is. The rest is only glare. And that's why the sun can be blocked by small objects like a lamppost. Anyway, the sun should be about the center of the glare. It is 52 degrees right from McKeegan's camera and 128 degrees from Duffy's. Let's trace again the lines of sight. 200 meters. 400. 1 kilometer. The overlap starts at about 2 kilometers. 3. 4. 5. Do we need to continue? So again, what this means is that the sun was too far away. No LED screens, no studio, only a vast landscape and a far, far away sun. But where were they then? Is it possible to have some proof that they were really in Antarctica? Yes, there is a way, if we have a model. What is a model? Well, putting together a salad bowl and a flashlight might fit some of the definitions of the world model, but that's not what we mean. In science, a model is a mathematical description of the nature. With a model, we can identify variables and parameters that are relevant to whatever phenomenon we want to display and understand how it depends on those variables. Gleason's map is regarded as the flat Earth model, however, it is not for a number of reasons. But that's a topic for a future video.
The globe model also predicted the exact elevation angle of the sun based on where we were in Antarctica and what time of day it was, including the up and down wave pattern motion throughout the day. And if that's not enough, the globe model also says that at the geographic poles, the South Pole and North Pole, the sun's elevation angle will not have any visible change in a 24-hour period, meaning no wave pattern.
So let's take this phenomenon that Will Duffy has just explained. On a spherical Earth, during the correct season, sunlight arrives at an angle relative to the Earth's rotation axis, creating a midnight sun. Let's put an observer on the pole, exactly on the place where the rotation axis is. When the Earth spins, the observer remains in the same position, so the angle to the Sun does not change. As a result, he will see the Sun always at the same angle respect to the zenith. Let's put now our observer some degrees away from the pole. Let's call that angle phi. At noon, the zenith is slightly tilted towards the Sun, so the Sun will be seen higher in the sky. After half a spin of the Earth, it is midnight. Now the zenith is tilted away from the Sun, so the Sun is seen lower over the horizon. That explains the wave pattern that Will is talking about. Now, the power of a mathematical model is that we can link the amplitude of this wave pattern to the angle phi that we have defined previously. Remember, the angle phi represents the angle we are away from the pole. Measuring the same angle from the equator, what we have is the latitude where we are. On the other hand, the angles from the zenith at noon and midnight are related to the elevation of the Sun respect to the horizontal. So we can predict that if we are at some latitude, then the wave pattern will have an amplitude, given by the difference of the elevation angles of the Sun between noon and midnight. And the other way around is also true. If we have a wave pattern of this amplitude, we can know the latitude where we are. Where can we get the elevation angles from? First, we have West-Wallace's sundial, or as he calls it, the geranometer. It is a homemade device that measures the elevation of the Sun. If we plot the elevation as a function of time, we can clearly see the wave pattern. We can see that the elevation at noon was about 32.4 degrees, and at midnight it was 10.1 degrees. But it's not the only source of data. The same data can also be extracted from the 360 cameras from McKeegan and Duffy. From McKeegan's time-lapse, we get an elevation of 33.3 degrees at noon and 12.98 at midnight. From Duffy, we get 33.2 degrees at noon and 13.4 degrees at midnight. We can now calculate the latitude from the angles of elevation. Different devices, different ways to record the same data, but we get similar results, within 1 degree of accuracy. Combining all the values into a single one, the average value is 79 degrees and 35 minutes. And the correct location, according to MC Toon's GPS, was 79 degrees 44 minutes. Quite a very good approximation. Now, you can think that if these guys were faking a sun, of course they will take into account lines of sight, the wave pattern, and all these fine details that no flat earther really knows how to look into. But on the other hand, it seems that they were clumsy enough to mess up with the shadows and distortions of the sun. So either we have some kind of Schrödinger fakery, too smart and too dumb at the same time, or simply the flat earthers don't understand the shit. Bye bye.